Welcome everybody to the presentation of our CIDR paper, which is about a new class of so-called architectureless database management systems for scalable data processing. The paper is a result of a collaboration of multiple authors and my PhD student Tiemo, who is the main author of this work, and I will be presenting the paper. Today, as we all know, scale-out database management systems are widely being used in industry and are not only popular for on-premise installations, but also dominate the cloud market. The main reason for this dominance is that scale-out database management systems typically offer an economic more viable option when compared to scale-up solutions, since a cluster of not so expensive commodity machines can be used for handling large amounts of data, instead of using one potentially very large and thus highly expensive machine. The two predominant architectural models that are used as backbone for building scale-out database management systems are the shared nothing and the shared disk architecture. While in a shared nothing architecture, each node provides compute and storage in an aggregated manner and has the autonomy over a partition of the data, in a shared disk architecture, the compute and storage are disaggregated and compute nodes have access to all data via a shared storage layer. Hence, shared nothing architectures are ideally suited if the workload and data is well partitionable. However, the performance of a DBMS that implements such an architecture typically degrades under skewed or hard to partition workloads, where some nodes are being idle and others are being overloaded. On the other hand, the shared disk architecture tackles many of these drawbacks by using a shared storage. However, the disaggregation of compute and storage not only has advantages. One major drawback of disaggregation is that data always needs to be pulled from the storage into the compute layer, which might cause higher data access latencies. An important observation that holds true for both architectures, though, is that the choice of which architecture a DBMS implements is a design time decision, and hence the architecture-dependent characteristics, such as those mentioned before, are more or less statically baked into the core of the DBMS and cannot be altered at runtime. As a result, the fate of the DBMS is often dependent on the architectural model a DBMS has initially chosen. For example, database management systems such as SAP HANA or Teradata, which have opted for implementing a shared nothing architecture, are typically used more intensively for on-premise scenarios where the workload is known in advance and thus data and queries can be optimally partitioned across a fixed set of resources. However, shared nothing database management systems have a hard time to make their way into the cloud, where the workload is less predictable and hence elasticity and robustness against skewed workloads, for example, are key requirements. To explain this dependence on the architectural model, let me give you an analogy in the world of my son, who's really into cars these days. He clearly would agree that a car that is built for racing tracks excels when being used on a racing track, similar to shared nothing DBMS, which excels on workloads that are well partitionable. However, a racing car really sucks when being used off-road, which is a situation where it was not designed for. Hence, in this paper, we propose a radically new approach for building scale-out database management systems, which takes a completely different route. Instead of hard-baking an architectural model statically into a DBMS at design time, we propose a new class of database management systems which can adapt their architectural model at runtime to ideally support a given workload. Adaptability of a DBMS at runtime has clearly been studied already in the past, for example, for adaptive query execution. However, different from approaches such as EDIs, which have focused on adaptability on the micro level of individual components, our approach aims for supporting adaptability more holistically across components. As a result, an architectureless DBMS can either mimic classical architectures at runtime or form completely new architectures such as hybrids of shared nothing and a shared disk architecture. In the following, Tiemo will next discuss the main ideas on how such an adaptability of the architecture at runtime works and report on our initial results of building such a system.
Thanks, Carsten. So the main idea of our approach is that in an architectureless DBMS, each database node is composed of a set of generic components called AnyComponents or ACs for short. The key to adaptability at the architecture level is that an AC can act as any DBMS component at runtime. For instrumenting these generic components and to coordinate the overall execution on the DBMS, each of these ACs consumes two streams, an event stream and a data stream. While the event stream encodes the operations to be executed by the AC, the data stream delivers the required state. For example, If an AC is instrumented by a compile query event, along with the required metadata and statistics from a database catalog, an AC can act as query optimizer. As output, an AC can produce new events and new data, which are then shipped to other ACs. In the example, when an AC executes a query compile event, this AC creates a set of new events as output that trigger the execution of individual query operators. These new query execution events then instrument ACs to become workers for query execution, executing query operators such as filter, join, or aggregation. A second key aspect of the architecturalist DBMS is that by simply changing the routing of event and data streams, an architecturalist DBMS can adapt its architectures at runtime. For example, for executing OLTP queries under a normal load with fixed resources, the event and data streams could be routed such that the architecture forms a traditional shared nothing architecture. If the overall load increases, it might be beneficial to add more nodes and reroute the event and data streams to additional resources. To make use of additional resources in AnyDB and to deal with the increased load, some operators can be executed by additional compute resources simply by rerouting the data and events, moving towards a shared disk-style architecture. While this adaptation based on event and data streams seems to make sense for OLAP-style workloads, as discussed before, an interesting question is if the same model can also be used to efficiently execute OLTP workloads requiring coordination of concurrent transactions. I would like to walk you through an example showing how we execute OLTP workloads in AnyDB. We see two transactions, X and Y, that execute different read-write operations on data items A, B, and C. The main idea of mapping these transactions to our execution model is shown on the right. Similar to executing OLAP queries, individual read-write operations of the transactions are executed by sending events to ACs, while the order of operations within a transaction is being modeled as event stream. For example, for executing an instance of transaction X, say X1, we would first trigger an event to execute the read-write operations on A using one AC. This AC then creates a follow-up event that triggers the execution of the read-write operations on B. An interesting question is now how isolation of concurrent transactions can be implemented in this execution model. A naive solution to coordinate the execution would be a distributed log table. However, a global log table would lead to high latencies and low throughput since each operation must access the global log table. Hence, in AnyDB, we suggest a different route. Instead of using a global log table, we make use of the fact that we represent the workload as a stream of events and use event ordering for concurrency control without any need for locking to provide isolation. For example, for executing the transaction instances of X1, X2, and Y1 in the example concurrently, we must guarantee that the events of X2 cannot overtake the events of X1. Otherwise, the resulting schedule would be non-serializable. Let me now show you some initial experimental results. Here we see an experiment where we compare AnyDB that can adapt its architecture to an open source DBMS which uses a static shared nothing architecture. Over the course of this experiment, we varied the workload from partitionable OLTP workload over skewed OLTP workload to an HTAP workload. In the first phases, where the workload is well partitionable, the shared nothing DBMS excels. But AnyDB, since it can mimic the shared nothing architecture, can achieve almost the same performance. Over the course of the experiments, we see a clear benefit of AnyDB. Under a skewed OLTP workload, our execution model allows AnyDB to make use of all available resources, while the shared nothing DBMS suffers from load imbalance. Also, since we avoid locking with our novel streaming-based CC scheme, AnyDB is less sensitive to contention. When executing the HTAP workload, AnyDB excels as well, as the sporadic OLTP queries can be executed on additional resources handling the increased load. Let me now wrap up. In this talk, we have presented our vision of a new class of so-called architecturalist DBMSs, where the main idea is to defer the architectural decision to the runtime of the system by using our flexible execution model with event and data streams. In addition to the topics covered in this talk, many more details are being discussed in the paper. For example, on how we enable efficient movement of state to ACs by proactive data shipping. Moreover, there are many other open opportunities that could be enabled by a system such as AnyDB. For example, the flexible routing opens up many other forms of adaptation, such as to include heterogeneous computation at runtime. Furthermore, we think that the stateless execution model could also be an interesting alternative to build serverless DBMSs on top of function as a service. Thank you for your attention, and I'm happy to take your questions now.